Welcome to another lecture in the series of Advanced Material and Construction. Today it is about a call for action. What we should do as designers and architects in the field of material research and design. And we are called for action because the situation is alarming. As part of the construction industry, for example, we are responsible for up to 39% of carbon footprint and global emission. Adding to that, if we go on with our consumption, there will be nothing left. We are in a critical situation, an alarming situation of material depletion and resource criticality in quite a few areas and domains. A complementary image on a sensorial emotional level is not less alarming. There has been declared a loneliness epidemic that is worldwide, and its effect is not less critical or important than any other physical epidemic. As we know, for example, smoking or alcoholic drinks. So this alarming loneliness epidemic is connected also to us as material designers and architects, because the ties between us and the world are primarily sensory and just secondly mental or cerebral. How could we feel a sense of belonging having been cut off from the full sensory relationship with the world? And this sensory relationship goes through physical environment and material. That is our activity, our profession. Now we know that one could find compensation in consumption and shopping. Well, look at this alarming image also, ecological footprint of consumption worldwide. Continents are here disproportionate according to the level of consumption and waste generation. And not surprisingly, the strongest economical places, North America, Australia, also are the one responsible for the largest consumption level and waste generation. We live in a relentless materiality. This relentless materiality of Black Fridays, of frenzies, of the last television set released on the market, or the recent iPhone that we just have to buy once again. And we need to have a counterbalance, to countermeasure as designer to this relentless materiality. And to reclaim materiality to suggest something else, to suggest an alternative. With this call, we actually opened the semester with the text of Schroepfer saying that we as architects should be unsatisfied with whatever we have offered as existing materials and components as they are today. We are called for an active involvement as architects in their development, in their processing, in their fabrication, in their adaptation to our contemporary needs. It's an obligation, but also a privilege in a way. And if we look at this mythology of the Tower of Babel, we see that actually these were the first material developers. Well, they took the brick instead of the stone. They invented the combination, the first combination, engineered combination between found material, made this composite material of a brick, and that was their new stone, and their tar was their new mortar. And with that, they could reach the heavens. And they have begun to do this, then nothing they plan to do will be impossible for them. Well, at the end of the story, there is a celestial power, and this does not happen. But we, if we go on with this mythology, as material designers and material developers, have this extreme power in hand, and we have an opportunity. With this power in hand, we can consider ourselves as lucky, very lucky. We are at the point of opportunity. Look at this mapping of digital transformation along history with relation to technology. So it starts with a focus on transforming material from Stone Age to Bronze Age and Iron Age. It's about transformation of the materials themselves. Then it moves into transforming energy from water power to steam and electric power, and today it is definitely about transforming information. But we are at the point where we get back and we have this transformation of information as a power that could get back and once again transform material in a very substantial and profound way. This profound way can get all the way down to the nanoscale. So we see here the scaling of a lattice miniaturization. It gets down from centimeter scale to nano scale, the microns, and this minute control of the structure of the material, its internal structure up to the nano level, is actually what will define the behavior and the performance of the material as we require it. it actually calls for a new form of knowledge from us designer. It calls for interdisciplinarity. Let's have another look at the diagram of the Bauhaus that we have introduced already before. So on the left, we have the original Walter Gropius diagram that we saw with materials at the center forming the core of the education of an architect and a designer. On the right, we have the new Bauhaus curriculum from 1939, once the Bauhaus had to move. And here we see an element that is introduced, a very important element, is science. So along with the observation of nature and nature study, we have sciences introduced into the education and the formation of the new designer, the new architect, actually calling for new forms of knowledge. Looking at the contemporary New European Bauhaus, the EU initiative of 2021, we see three poles. It starts with together. So again, it's interdisciplinary. It's called for a collaborative action of different disciplines in the domain of the beautiful, in the aesthetics, in the material culture of design and architecture to achieve goals of sustainability for a higher purpose of creating a better world for the future for us all. So another diagram here that actually tracks this relationship shows art and technology from the historical Bauhaus through art and science in the School of Design of Chicago, and finally concluding with the New European Bauhaus with the four poles where we have not only science and technology but also art and the newly added sustainability pole. So that's the four poles of the new forms of knowledge and the new forms of actions that we are called for today. Well, because we are living this Bauhaus culture, we have recently first-hand experiments and experience with material. We are hacking, we are DIY. We are in this world of material revival, and the orderly world of material libraries, a ubiquitous and organized reality, is no longer sufficient. And we are called again to create and transform this directly firsthand. With these new forms of knowledge entering our disciplines, we have the appearance of new hybrid designer, new aspects of design coming into light. We'll have the designer biologist, for example, in interaction with botanists, biologists, geologists, to find alternative modes of fabrication, such as biofabrication, or the designer maker, some kind of a mechanical software engineer in quest for open and adaptive systems and material, or the designer detective looking for a systemic, holistic approach in quest for energy neutrality, like some kind of a material scientist, for example. So all these facets are the new agents of change, the new aspects of the material designer. And they actually include elements that we have identified before. They will reside on the DIY trend and the fabrication, digital fabrication that has entered as well, craft, digital craft, the interest in experience, sensorial experience in the material realities that we create, and the responsibility and awareness of sustainability, of course. These material designers are agents of change. They can design, redesign, reform, reuse, and redefine materials, giving them an entirely new purpose. These actions have the ability to implement positive social, economical, political, and environmental change across all sectors towards a more responsibly designed future. So we have here an expansion to the maximum of the role of the designer. And in parallel to that, we have the expansion or the positioning of the role of the material. We have started the semester with that, with this repositioning and the new materialism. We are no longer imposing our wish or our will on a passive element of the material in a godlike action, but rather we allow the materials to have their say in the structures we create. We have these two parallel tracks of evolution. On one hand, the redefinition of the role of the designer, the expansion of a territory, and in parallel, the material agency or repositioning of material. In their convergence, they lead into this new kind of discipline, which is material research and design. So what is it exactly? Is it magic? It is alchemy? Well, not really. It's more of experimental research that is based on physical experiments, often also involving digital tools such as simulation for optimization or digital fabrication. So rather than a magic or kind of a mystery of alchemy generating and creating new material, I'd rather suggest the analogy of a puppeteer dealing with a manipulation of matter in a controlled manner in order to obtain a controlled, indirect but still controlled, required outcome. The required outcome could be a specific performance or a type of behavior or aesthetics, but it's a controlled outcome and it's done indirectly. And it's done indirectly through control of variables or channels or restructuring of existing elements. So we will take the model of Schumpeter in economics, suggesting that innovation comes from new combination. Innovation consists from new combination of existing elements, kind of channels that you are restructuring or redirecting, identifying the important parameters, the significant parameters that you want to play with to create your new system and get to your controlled required outcome. And we understand that it actually resides on existing conceptual platforms. So, for example, parametric design. I've mentioned the word parameter or the logics of variation, as we see here in the work of Greg Lynn, Flatware, very early work for Alessi. Here he introduces the notion of endless variation within one system or one topology. And the control over these variation is done through parameters and their variables. So all of them are actually a reconfiguration or new types generated from one single topology. And that's the basic principle of parametric design or parametricism of Schumacher, suggesting that it's everything, all composition, all elements are subject to modulation via their variables. So we have a system with variables and we modulate the outcome. The logic of material variation, the modulation of the material variables, actually refers back to the discipline of form finding. So although it's ancient and from Gaudi and maybe earlier, this discipline is mainly associated with Frei Otto, a German engineer that from the 60s onwards has been doing countless experiments, physical experiments, studying the self-organization and the natural behavior of materials to obtain shapes and structures. So his study here, he's classifying his experiments according to the generated form, from linear element to surface element, and even systems of space and time. But more interesting maybe is to look at this diagram where he classifies his physical experiments, the same experiments, according to the generating forces. So the forces applied gently and indirectly, forces applied on the material to obtain the required controlled shape. So tension, compression, and bending are the three categories where the materials are put under these forces, and under self-organization, the required control shape is emerging. This is done through countless number of experiments. For example, here, the bubbles clustering and forming polyhedral foams, or a membrane of viscous fluid simulating the behavior of complex membrane systems just by external boundary conditions, as we see here. Another example would be the hanging membrane, the studies of the way membranes that are hanging under gravity behave. Here also we have an example on the right of Heinz Isler, another engineer, specifying and mastering this tradition. And with the study of the hanging membrane and their manipulation and their modulation, they get the precise image of the resulting shell once inverted and under compression. Still in Stuttgart today, this discipline of form finding is taken to the next level, involving computation in the ICD, the Institution of Computational Design. These research projects are expressed as impressive large-scale architectural pavilions, always starting with the material study with form finding. Oftentimes, these pavilions start with a biological reference, a model that is transposed in a biomimetic process into the architectural realms. All these construct together a material system. It starts with a study of the material and its behavior. For example, here, this pavilion of natural composites starts with a study of the behavior of the flax fiber. And from the behavior of this material and the building of components, variants of components that are parametrically controlled, comes the level and the step of material computation. Material computation also involves the simulation of material behavior, which is essential when constructing and designing such elements based on material system with indirect parametric control of the result. So the elements of form finding, a biological reference, material computation, material simulation, gives you a system from which you can build elements such as this pavilion, a singular result, a singular element out of a system that involves all the way from conception to material manipulation and fabrication process. If this notion of a material system might be still a little vague, I suggest to clarify this through opposition to things we classically know. So instead of focusing on one product, the design of one single element, for example, the display of one time of the day, we will be designing and building the engine behind it, the system of components that are interrelated that would enable the display of all times of the day, for example, the specific time chosen here. Instead of debating about style, we'll be constructing the language behind it, the code or the protocol that will determine the expression as a style. And instead of focusing on one single element or masterpiece, we will be shifting towards the multiplicity, the variance, and a multitude of expression of one single principle. To obtain a material system, we go through a process of material research, and that could also be referred to as material tinkering. And we have various types of tinkering that we identify. One could tinker the formula, play with the ingredients of the recipe to obtain a final result. The other could be tinkering the process, how the combinations of these elements, their interrelation and their processing leads to the desired result. And the third would be tinkering applied to the direct sample to obtain, again, a desired behavior or a characteristic. I suggest to follow these three types of tinkering through a student project started here at the Technion as a group project in 2017. So they were studying a new type of cement mixture, of phosphate, and together with water and sand that we traditionally know, they combined carbon fiber as reinforcement and polyester to the mixture. So altogether, this formed actually the formula, and they were playing and tinkering around this formula to obtain a desired result. So with the variations of the value of these ingredients, you get material effects. More water, you get more workability. If you increase the level of sand, you get strength and stiffness, and similarly strength and flexibility with the fiber. So the final composition of these elements were tested time and again with a desired result. Here was a thin shell without external reinforcement, extremely thin, thanks to the characteristic of the formula and the balance between flexibility, stiffness, workability, etc. So beyond this very tedious stage of tinkering of the formula, they went into tinkering of the process. So you have your mixture that would behave the way you want. It can create flexible, it can create thin and efficient shells. But now molding those was done not in a traditional rigid mold, but in a flexible mold. And this flexible mold was mostly adapted to the specific characteristic of these this specific cement mixture, as it was fast drying and it enabled the generation of these types of shells over a hanging membrane of textile, a flexible mold. And changing parameters of the system just with these wires changed completely the configuration and the resulting morphology. So having also a flexible molding system with a quick drying strong cement mixture. And together, combining both elements, they could define a material system that would also even thereafter digitize to create a design tool. Thereafter, Ryan took this as a basis and developed it as a final project, tinkering in formula, process, and sample, taking it to rotational molding of concrete, so combining elements from completely different worlds to create a novel brick, a novel building block, which is a void, thin-walled cement building block by rotational molding of the concrete, a specific concrete mixture, combining all three elements and suggesting novelty in all aspects in the fabrication process, in the formula, and in the resulting building block. This combination between the tinkering of the formula, the recipe of the Fostman concrete, the process of manufacturing in rotational molding, and the sampling with a flexible membrane that serves as a mold is a very good example, actually, of a holistic project of material research that leads to innovation. We have a structural element that is not only structural but very light, and also enables easily complex geometry in a low energy and sustainable manufacturing process. We will follow and have a better look on material research discipline, what it is exactly, how it is done. And I suggest to do that through other student projects. You could better engage and relate to it, see how accessible it is and how this could relate to your studies potentially as well. We'll have a look on several material systems, and we'll start with the minerals. This project, Chaîne Opératoire, starts with the manufacturing process of metal, of steel, and a reconstruction of this process and the way it was done in ancient times. So everything here is done by hand. It's not industrial, it's not mechanical. It starts with the building of the firing kiln and the collection of aggregates that are very rich in ferrous elements. They are collected in the desert in the southern part of the country. Once placed in the kiln, the metal manufacturing process starts. And apart from the metal that is manufactured, which is the process itself, some waste is generated. This waste is called slag, and this is the lava-like that you see coming out of the kiln during the firing process. This material, the slag material, is waste material, and nothing is done traditionally with this waste material. This is exactly the starting point of this project. So with the slag material, the student is taking this as the raw material, the starting point of the material experimentation project, and he tries to transform it, to manipulate it, to make it more glassy, have more plasticity, to be more workable, to reduce the energy on the transformation and manufacturing process. And here starts a long process of material experimentation with the formula of the material itself, playing around and trying to get a more glassy element that will be more workable, that will be light, that will be low in energy. From these combination of silica, sodium, kaolin, bentonite, and calcite, various amounts and combination and recipes, a few are selected to go forward and to serve actually as the material with which the final elements were generated and manufactured. The inspiration was drawn from archaeological elements due to the source of the project, the historical process and manufacturing of these objects. And you see the lightness, for example, of this element, of this material, is thanks to the introduction of sodium in the mixture. And it is finally a kind of in-between element. It is porous, it is light, it is ceramic, but it has a very strong metallic effect due to the ferrous component that are very high in this mixture. We'll continue in the kingdom of minerals. Here, it's a project about clay. While the previous one was about the ancient and traditional manufacturing process, here it is about contemporary fabrication techniques, the CNC machine and its interaction with clay. So tilling in clay is actually about this meeting, this interaction, this physical friction between the rotation of the spindle of the CNC machine, the spinning motion, and the wet clay. The outcome of a simple path, a line, for example, could be a very complex texture, and that's actually the result of the parameters of the CNC path and the self-organization of the wet material, which is viscous. So this dynamic process leads indirectly to the generation of a texture, and the control of this texture is done by the control of parameters of the CNC machine. On the basic principle of a path generated in the wet clay actually starts a long series of experimentation trying to trace and understand the connection between various parameters of depth, speed, angle of the CNC spindle and the wet clay and its condition, its amount of viscosity, the type of clay that is used, all this to control indirectly the resulting element, the resulting three-dimensional organization of the material, the resulting texture as we see here. We'll stay with the marvels that nature has to offer. This time the natural material is living, it's growing, it's a plant. It's an aloe vera plant, and the topic of this exercise is the shape morphing due to moisture absorption. The structure of the aloe vera leaf is a bilayer structure, that is, two layers on top of each other, each of them with different characteristics. The outer layer is low on moisture content, and the inner layer is higher on moisture content. Now, upon drying, it shrinks, but it shrinks differently. So the outer layer does not shrink at all, or almost no shrinkage, and the inner layer shrinks considerably. The result of this differential shrinkage is three-dimensional. And this is actually the process of shape morphing. So with this idea in mind, they started browsing quickly to find the appropriate material to work with for this process. On the right, you see the list of materials they were testing: rice paper, zucchini, cucumber, finally arriving to the choice of aloe vera. And on the left, you see the list of materials they were choosing as moisture-absorbent material. Eventually, it ended up in this process of the selection of aloe vera leaf as the membrane, the base membrane to work with, and the application of sodium, salt, to absorb the moisture and generate the emergent shape, this movement, the motion that you see here, self-shaping. Based on this idea and the proof of concept, here comes a long series of experiments to isolate the different parameters and understand how these affect the resulting shape. Here, for example, you see the alignment of the absorbing material along the fiber direction of the plant. And on this basis, you have a long series of experiments, each testing separately an aspect of it. For example, the location on the membrane itself, the width of it, the size, the height, the amount of material that is put, the effect of time on each of these elements. So each of them mapped separately to have a good understanding of the rules of this system. And once the rules of this system are mapped and understood, even numerically, then you could go to computation and have a code, in this case a parametric grasshopper code, that represents the process and the effect of the different parameters over the resulting shape. The extraction of the material is manual and simple. It's here demonstrated. So it starts with cutting the leaf and separating it, and here you see the jelly-like material and the outer skin. One main factor is the outer shape, the boundary shape of the membrane itself. And of course, another pattern, which is the pattern of the application of the absorbing lines of the salt. And the careful combination of those and the control over the resulting shape gives us complex morphology, very finely tuned. With this kind of catalog or the control over the resulting typologies and the parametric code, now came the application, a playful application. And as this material is edible, it is a plant that could be eaten, they chose the world of the kitchen or the culinary world, the world of cocktails. And this is placed as part of the performance that is taking place around the world of cocktails and mixology. We stay with fiber-based materials, but we move to textiles. And here it is about, again, the complex morphologies that are so easily generated in textiles. The magic here is shrinkage. It's actually the same principle as we see in nature, because the magic of these leaf or petal and the intricate undulating form that it takes, the complex membrane, is generated by differential growth, which is exactly the same as differential shrinkage. How is it done? Well, it's transformed into a system definition that is a membrane, a piece of fabric that is stretched over a frame. And over this stretched membrane, a pattern is applied of a stiff material. They are glued together, and once the fabric is released, well, the fabric goes back or wants to go back to its original size, but the stiff element stays in its original size, and the result is a complex three-dimensional shape that is generated. Now, it's all about understanding and identifying the parameters of the system, and it goes through a long series of physical testing. So on one hand, it is material testing, finding the stiff element, the stiff material that is adequate for this process, for the scale of the process, the base material that is most suitable, and the amount of stretching and the way of stretching, etc., etc. And on the other hand, it is a geometric research process where patterns are tested, and the result is not always as easy and direct or linear to predict. So here you see, for example, the pattern that is placed over a lycra, stretched unevenly between the two axes, and a polypropylene that is glued over the stretched material. Once released, it forms this incredible, unexpected shape. Once constituting a catalog of patterns, simple linear patterns, and their complex, unexpected morphologies, scaling up is also another challenge of this project. And you see here a prototype of the scaled up element on a larger scale. On the success and the catalog generated by this project, a series of other student projects continued in the following years. So here, taking it a step forward, again, a pattern that is stiff is applied on a tensile membrane on lycra. Here it is done by 3D printing. But the step forward that is interesting is this idea of what is called inverse design. So not only predicting the resulting shape, knowing what will be the outcome of a linear simple element that you apply on 2D and what will be the morphology on 3D, but also going it in the reverse engineering. That is to say, there is a target, there is a shape that I want to obtain. This is my target, my aim as a designer. And I know, I can understand what would be the pattern that I have to put on the fabric, on the flat fabric, in order to obtain it naturally by self-morphing. So we have the volume of a foot here that is wrapped with this self-morphing membrane, and it is wrapped with these features according to the pattern. So 3 different models, and you see every area of this wrap, of this shoe, is different in morphology, and it is obtained with these features that are controlled. Yet another project afterwards, taking it one step further, is to talk about performance. So not only the pattern and the way it generates a morphology, but the patterns and their properties, their typical properties and their performance. So this catalog is generated and a few behaviors are identified. Amongst other is the absorption, the energy absorption potential of such patterns and such 3-dimensional structure. And the different patterns are evaluated according to that. Now, the different parameters of each of the pattern is also manipulated and the variables are placed as such to obtain optimal result. It could be the width of the elements, the distance between those, the thickness of each of the elements. This system is also 3D printed over the stretch fabric. And once this is placed in a parametric code, with identification of the different variables that we want to change, the sliders, according to the outcome that will be generated, well, you have an assembly of patterns and their different performance behavior, their different potentials. And once all this is set, you can also apply it to a required application. Here, for example, to be a shape stress absorbing element for motorcycles. We stay with textile, not so much about self-organization, but more about manipulation of textile. So their self-organization means that you could do very little, very small and simple manipulation, low energy, low force action on the material, and get a very significant result in a 3-dimensional organization of the material. Blooming is just about this simple manipulation. You just pull through, you push the material through an opening, let's say a board with a hole, and you take a fabric and you just push it through with a stick. And the resulting flower is blooming. I'm not so much interested about the architectural system here, but more about the process. So initial stage of this process of a material research would be the identification of parameters. That's the most important stage, where you understand what are the important parameters that will affect your system or your result finally. So you establish a set of parameters and their variables. You understand what will be the significant aspect of this system. It would be the placement of the hole over the material. It will be the size of the hole, of the opening, with regards to the general size of your fabric. It will be the amount of material that you push through, etc., etc. Identifying those parameters and giving them values, and they're linking afterwards the resulting behavior, brings you to the understanding of the rules of the system you're trying to build. So you establish a catalog that links between the input and the output. If I change this, what happens to that? And with this catalog and the understanding of the rules of the system, you can thereafter go and build a code. And with this code, you can try and adapt this to a system, an array of these elements in a special organization here, for example. And this assembly gives you an ability for an application. Here, it's an application as an array of openings and a continuous fabric that is placed within this opening. So you can imagine patterns where you have this grid and you have a different amount of material pinching through these openings and the resulting shape. And in this case, the material that was chosen was stiff enough to result in also a shock absorbent kind of spongy-like surface. To conclude, this last project is still with textiles, but here with another material that is yeast. So the combination between textile and yeast gives us a composite material, and the students explore the constituents of this composite material and parameters of gravity, quantity, the effect of time, etc. The system they establish is very simple. They stretch a jute piece over the frame, they spread yeast over this jute piece, they remove it from the frame, and actually they hang it to give it a shape. So the hanging impregnated textile with a yeast paste, is going under self-organization. On the macro level, there is the formation of the shape under gravity, the draping of the material. On the micro level, there is the dripping of the material, of the yeast material, giving it texture. And here, there is a significant effect of time. This table is established where you see here, as an example, the amount of material on the column on the left and the viscosity amount on the top. And the matrix of the result is described on both levels, both the behavior on the macro level and the behavior on the micro level. So both general global shape and texture at the same time. And based on this identification with other parameters such as the hanging points or the outer pattern, a catalog is formed. Here it is applied to a garment, and this garment is afterwards segmented into different elements. These are the parts that actually constitute the vest or the jacket, and each of them is applied to which each of them are applied a different set of variables according to the result that they want to get. So they want to get a dual result. On one hand, a shape, a three-dimensional shape that would actually adopt my shoulder or my elbow or different morphologies, curved morphologies of the body. And in parallel, on the other hand, they have a desired texture that they want to obtain according to the different parts. And this is obtained through the parameters that they control of amount of material, times, temperature, etc. Through a variety of students' work, my interest was to demonstrate the process, the attitude, the approach, and the tools that are used in such a kind of a discipline of material research and exploration, understanding the parameters of the system, their identification, coding, and finally application. And it's maybe best to conclude with an architectural application in the crafted hand of the master of Shigeru Ban. For years, he's been developing the use of cardboard in his system, and he's applying those to meaningful architectural actions as disaster relief here, for example, shelters in Ukraine. So this simple system that he started developing 20 years ago, still elaborating it today, changing the joint system, changing the processes, changing the finishes, changing the catalogs and the application according to the time, according to climate, and according to other materials that are to be joined with this system. You see the joint is changing each and every time, but the application stays similar and the same within this very unique material system. The unique material system of cardboard tubes is taken also to architectural application in parallel here in combination with wooden joint, complex wooden joint. Together they form a very intricate and complex truss system made of very light element of the cardboard. And finally, to conclude, he marries those cardboard tubes with joints that are from metal in two different types of joints for different applications for architectural masterpieces. So with this inspiration of architectural application of material innovation and research by the hand of Shigeru Ban, we conclude this session and the call for action for your activity and action in the field of material research and material design. Thank you.